Hello, everyone. Welcome to our fourth keynote speaker session. I'm very pleased today to have with us Dr. Ahmed Fahmy. Dr. Ahmed, can you hear us?
Yes, perfect.
Okay, thank you. We're very happy actually to have Dr. Fahmy with us. Dr. Fahmy is our former colleague, and he's currently with the Department of Medicine at Harvard Medical School. For those of you who don't know Dr. Fahmy, he spent actually quite a good amount of time with Nile University, I think from 2008, if I'm correct.
Yes, until 2016. Yeah.
Till 2016. And during the same time, actually, he was with the Faculty of Engineering, Department of Biomedical Engineering at Cairo University. Dr. Fahmy also acted as director of the Communication and Information Technology program at Nile University, where he co-founded the Medical Imaging and Image Processing Lab as a part of the Center for Informatic Science. And also he's the co-founder of the Big Data and Data Science Diploma, the famous diploma of provided by Nile University since 2015. Dr. Fahmy received a bachelor and master's degree in biomedical engineering from Cairo University and a master's and PhD in electrical and computer engineering from the Johns Hopkins University in the US. His research interests include medical image processing and analysis. And to my knowledge, he has been focusing on the applications of and technologies of deep learning in the area of medical image processing recently. Dr. Fahmy also serves as a reviewer for several journals, including Cardiovascular MR and Magnetic Resonance in Medicine, MRM, and these are quite good journals in the field. He received a Gold Star Reviewer Award from GCMR Editorial Board and Distinguished Reviewer from MRM Journal as well. Dr. Fahmy also received a state award اللي هي جائزة الدولة in Engineering Sciences from the Egyptian Ministry of Higher Education من وزارة التعليم العالي والبحث العلمي. So this is a quick introduction of Dr. Ahmed Samir, and I leave it to you, Dr. Ahmed. I'm very keen to hear your today's presentation.
شكرا. هشغل الفيديو عشان بس يبقى or less virtual يعني. السلام عليكم. شكرا دكتور محمد على الانترودكشن. أنا حقيقة I'm very happy إن أنا to get the chance to meet with you and the colleagues and the students. Like reunion after 4 years or 5 years. So yeah, let me share the presentation here. Can you see the presentation?
Yes, yeah.
I'm sharing it.
Yeah,
okay.
Yeah, we can see it. Thank you.
Okay, thank you. So the title of this presentation is Deep Learning in Medical Imaging, Practical Challenges and Opportunities. So I will focus on the practical aspects of deep learning in medical image analysis. So let's see what's... Yeah, so I'll start with a brief introduction to medical imaging. So medical imaging, in general, it's a process of creating visual representation of the interior of the body. So it allows us to get to know what is inside the body without really open the chest or open the abdomen to see what is in there. So it's minimally invasive. And the purpose is diagnosis. So evaluate the health or the disease status of a patient. Prognosis, which is to predict the progress or regress of a disease. And it can be also used to guide interventional procedures like small surgeries or endoscopic surgeries. The modalities are numerous, include X-ray, ultrasound, CT, MRI, SPECT. So we have large set of data with variable contrast, with variable characteristics and can be used for different applications. So I would start with the very beginning, the analysis of medical imaging as it started. So in nature, it was subjective analysis, and still it is subjective analysis. So this is X-ray image for the lung or of the chest for a healthy subject. So X-ray images gives us information about the amount of attenuation of X-ray inside the body. So here, the lung appears, the lung in general appear black in X-ray images because there is less attenuation because it's full of air. Bones and myocardium or the heart or the liver appear bright because there is much more attenuation in these structures. So when experienced doctor sees this image, he says, okay, it's a healthy subject. So in case of COVID, for example, lungs are full of or containing some fluids which increase the attenuation to X-ray, and therefore it appear these regions appear bright. So if you see these two images properly, you can recognize that, okay, this lung contains more fluid than this one. So probably this is a severe case compared to this one. So this subjective analysis, there is no quantitative measures, there is no numerical value coming out of these images. And subjective analysis is used in not just in X-ray, in ultrasound, in MRI, in many imaging modalities. But it has a limitation that first, it lacks standardization. So it depends on the imaging protocol, the device that you are using to get these images, and the clinical setting itself. And more importantly, it depends on the observer, the reader, the radiologist. So we have two problems here. The first one is the inter-observer variability. So if you have two doctors with different training, different experience, and then you show them the same case, same image, then you get differences in opinion about this case or this image. And we refer to this as inter-observer variability. Also, if you have the same case and the same observer, and you show it to him or her for evaluation now, and then you show them the same image after 3 months or 1 year, then probably due to difference in mood or something, they will evaluate this image in a different way. So we have inconsistency or lack of reproducibility of the evaluation of medical images. And this causes people to move to more quantitative analysis to compute some numeric value from the images. So for ultrasound, measuring the diameter or the circumference of the head of the baby or the femur bone, this can produce some numeric value. It's quantitative, it's not subjective anymore, that may help to monitor the growth, the weight, the age, or estimate the due date for these cases. So it's a one step forward. However, there are more limitations to come with this manual quantitative analysis of medical images. The first is it's tedious and very time consuming. Probably in the ultrasound case, it's not very time consuming, but for example, in the heart imaging, like this is the heart, and this is cine MRI images of the heart. So you get 25 time frames for each slice. So if you have 10 slices of the heart, you get 250 images. If you want to analyze them, if you want to draw or take measurements from these images, it becomes probably impossible to do it in a limited time. I want to spend a few seconds on this image because we'll see it again in the presentation. So this is a cross section of the heart. This is the left ventricle. This chamber is responsible for pumping the blood to the entire heart. So it appears here as this ring shape. So dark part is the myocardium, the heart tissues, and the bright part is the blood pool inside this chamber. So when it compresses, it pushes blood into the entire body. So the first limitation is the tediousness and the time-consuming process involved here. The second problem is it's manual quantitative analysis. So it's subjective. Somehow it's subjective. Because if you give the same image to two different doctors, probably they will differ in their delineation of the interior or the exterior borders of the myocardium. So this means that there is a need for automated quantitative analysis to properly replace or to mitigate this observer-related variability of manual analyses. And this takes us to the role of deep learning in providing accurate and fast analysis for medical images. So deep learning has been used or proposed to solve many problems or to automate many processes in almost every single stage in the life cycle of a medical image, starting from patient scheduling, collection of the images, reconstructing the images from the raw data acquired by the device, segmentation and analysis of the images, and then properly classification of patients or automatic generation of reports from the images, and also prognosis. In this presentation, I will focus on the segmentation of medical images. So what is deep learning? Just very brief introduction. I know that you know much about deep learning, probably more than I do. So I will just give a very brief introduction. So deep learning is advancement of old concepts. It's not a new thing. It builds upon development of the perceptron in 1957, neural networks starting in 1980s. And the basic operation is a weighted sum of some input values and a nonlinear functionality. So this is the very basic operation. You have, for example, input data, you input to the model, neural network model. You have some weighted sum, like a multiplication of some weights, some variables, and then you pass it to a non-linear function, and then you get the output. Probably the output is to classify this patient based on the input data as healthy or diseased, or the severity of the disease. And the key issue here is how to estimate the weights of a neural network. So these weights are they determine the learning characteristics of this model. So the word learning means that we need to estimate these weights. And usually we do it learn by example. We provide the network with input data and the corresponding output for few examples or for some number of examples or patients. And then through backpropagation algorithm or other variants, you get estimation of these weights. The word deep means that employing a larger number of nodes, processing nodes, and also increased number of layers. So this is what's deep learning. I mean, the core of deep learning. So applying deep learning to medical images or image analysis in general is kind of problematic with this architecture. If you have standard image resolution 256 by 256, this means that you have more than 65,000 input values, input pixels. So if you adopt this architecture to process the input image, and probably you have 10,000 nodes in the first layer, just the first layer, you end up with 600 million weights parameters for the first layer only. This is impossible to implement, not just because of the computational resources required, but also because we don't have this much data set. We don't have this much examples to teach this network the required task. So researchers start to see what is the most efficient architecture for learning 2D information, which is the visual cortex. They started in cats and monkeys, early 1960s, and with many studies. And the findings were that if an animal or a human looks at some face, then the visual information is processed through a number of stages in the visual cortex. So at the first stage, edges and lines are detected. In the second stage, these lines and edges are combined or processed to generate or to identify shapes, circles, squares, rectangles. And then these shapes are processed in a later stage to identify or detect objects like noses, eyes. And then these objects are then processed to get or to identify faces. So it's multi-resolution or multi-scale processing of the input information. And the processes in the visual cortex inspired the development of convolutional neural networks, which revolutionized the way of processing visual information. So in convolutional neural networks, an input image is being processed through different stages with different scales, different resolutions. The main operation is convolution, which is a weighted sum of the input pixels. And at the later stages, or deepest stage in the network, you identify the global information, which properly identifies a person in this image. So why convolutional neural network made a revolution in image processing or image analysis? Let me give you just a simple example of one application, segmentation of tissue mapping images. This study was presented in 2015, and the target was to segment the heart tissues, the myocardium here, in tissue mapping MRI images. So the authors of this work, so the authors of this work proposed an algorithm that contained almost 20 stages of different processing, morphological operations, image segmentation, masking, whatever, weighted segmentation, different algorithms. And at the end, they generated this nice, actually these contours, I drew it. So, but they generated nice contours like this, one delineating the inner boundaries of the myocardium and the outer boundary of the myocardium. So the problem here is that you have to tune the parameters of each of these algorithmic blocks. And it takes probably years to arrive at this algorithm. So probably this is a master study or a PhD thesis. So corresponding to this large effort, if we use convolutional neural networks or deep learning to tackle the same problem, we find that it's probably much easier to do it if you have the required infrastructure and you have the data. So this is one of our studies. We worked on the same, almost the same tissue mapping images by MRI. We trained a convolutional neural network with a large data set of MRI images, and we provided the segmentation, the corresponding segmentation of the input images. And we trained the network for 1 day. To test a new image, we just feed the convolutional neural network with this image and find the nice contours in probably a fraction of a second. So the story looks very nice, very easy, very simple, no challenges. Instead of spending 1 year of doing a classical image analysis or processing, we can just do it in probably 2 weeks. But the problem is not that easy. And this takes us to the challenges, the real challenge, practical challenges of doing this kind of research. So in the next part of my presentation, I will focus on one heart disease, which is HCM. I will put some motivation of why we study this disease and the challenges that come with this disease, because there are other diseases that probably much easier to solve the problems related to it. We also focus on images by MRI, one technique called late gadolinium enhancement. And we will focus on segmentation of myocardium scar, the scars inside the myocardium tissues. So what is hypertrophic cardiomyopathy, HCM? What is this disease? Every while we hear in the news that some athlete or some strong guy has just passed away or was about to die suddenly. There was no known reason for his death. And analysis of these cases of sudden death in this population, in this kind of population, we found that, actually researchers found that more than 36% of all these deaths were attributed to a single disease, which is HCM. So HCM is a genetic disease. So people are born with this disease. But however, not all of them would eventually die. I mean, all of us would eventually die, but this population would not immediately die. Only a very small percentage of them, probably 1% or less, would die from this disease. So can we prevent these deaths, these sudden deaths? The answer is yes. We can prevent it using pacemaker, ICDs. However, we cannot place all these ICDs or pacemakers in all patients due to risk factors and, of course, the cost associated with this procedure. So researchers started to study the characteristics of this disease and try to predict the probability of an HCM patient to suffer from this major incident of sudden death. So they showed that presence of scar in the myocardium indicates a high risk of sudden death. More recent research showed that the scar volume, the amount of scar in the myocardium, is an important risk stratification biomarker. And this takes us why we use MRI, because MRI is a reference tool for imaging the scar inside the heart. Recently, we and other researchers showed that deep learning has a very strong potential to segment or to quantify the scar amount in MRI images, where classical methods fail to quantify the scar in MRI images. So this problem, we don't have a solution, automatic solution for quantifying scar in MRI images for HCM patients. And I'll show you why. This is LGE image. This is the heart, as we saw it before. Myocardium is dark, normal myocardium. The blood is inside here. It's a little bit bright. And scar is a very bright spots here. So in HCM, we to provide an automatic quantification of scar, we have problems, even for deep learning. It's real practical challenges. First, scars do not have well-defined shapes or borders. They come in different locations in the myocardium, different contrast. The borders are really not clear, so it's subjective. Segmentation of these scars is a current standard, like manual segmentation of these scars. And more importantly, which limits or a major challenge to deep learning is that you have diverse image contrast and characteristics, which result from the different imaging protocols and different machines being used at the different hospitals or imaging centers. So the variations is not only in the patterns of the scar, it is also in the nature of the images, in the process of collecting these images. So in order to train a deep learning model for this particular application, you have a number of challenges. The major one is the data set. So you need a large data set. You need thousands of images. You need it to be diverse from different medical centers, different scar patterns. You need to be balanced. The data set that you will use for training a neural network model, it should contain a balanced number of cases with scar and cases without scar. And the real challenge is to have this data segmented not by a student, undergraduate or something, no, by expert cardiologist, which is really difficult to have a cardiologist expert in this disease to go and segment these images. So I like this cartoon. It shows the problem, summarize the problem. You need large size data set, you need large diversity among them, and you need it to be balanced. But what we get usually is a small data set, diversity, moderate diversity, and it is inevitable to inevitable to get imbalanced data set, because usually normal cases are larger than diseased cases. And we have techniques for deep learning to deal with this: transfer learning, augmentation, and weighted loss function. However, these techniques, I'm not going to talk about each of them, but in general, these techniques fails when you have severe limited, that's small size data set, or homogeneous data set, or complete imbalance in data set, like 1% of the cases have scar and 99% do not have scar. So in this case, you need to come up with other ideas to solve these problems. So in our case, we try to do our best to do this. There is no the golden solution for everything, but you need to do the best that you can. So for the MRI dataset, we managed to get patients, HCM patients, from 8 medical centers, from Italy, from Canada, and from the United States. And we collected more than 8,000 images from different imaging protocols, diverse population, different patterns of scar. And we were fortunate to have an expert cardiologist who did a manual segmentation of all these images. Then we did something that, again, is what we just mentioned, that we reduced the variability. We reduced the changes or the variation inside the images, because we have images from different protocols. So we needed to normalize these images. We need to reduce the diversity that is irrelevant to our objective, which is the scar. So we needed to maintain the diversity of the scar patterns, the different contrasts in the different diseases or different patients. However, we need to limit the dynamic range of the intensities, and also to unify the spatial resolution of each image. We chose off-the-shelf UNet, 2D UNet. It's a state-of-the-art architecture for image segmentation. Of course, we did a lot of optimization of the parameters, hyperparameters of the network, the number of processing scales, and the number of channels, the learning rate, and all of this hyperparameter settings. And the results were very nice at the beginning, of this study. So this is examples for 4 patients. This is a manual segmentation, and this is the automatic segmentation using convolutional neural networks. As you can see, very good agreement between the contours manually and automatically generated for the inner borders of the myocardium, of the outer border, and also for the scar. However, we notice that we are underestimating the volume of the scar. So if you have a scar of 10 milliliter volume, then you predict its size as 7 milliliter only. So there was like 70% underestimation. So we thought that if we use 3D segmentation, we can improve our sensitivity to the presence of scar. So we said that, okay, we can use a 3D unit, and instead of training it with individual slices, individual images, we can train it using the entire volume, the entire set of slices that we have. One of my colleagues told me, okay, this is low-hanging fruit, just get off-the-shelf 3D unit, put the data, and you'll get results in probably 1 week or 2, and then you have a very nice paper. However, that was not the case. Why? Because we had a number of limitations that we had to overcome first. So the first is the computational resources. Moving to 3D, we have bigger architectures. You need computational resources. We did not have this problem. We were working on DGX1 NVIDIA workstation, so we did not have this problem, but it limited the batch size for our development. But the major problem was the dataset size. You may wonder, but you use already this dataset, this 8,000 images to train the 2D convolutional neural network. So why it could be a problem in 3D? The problem was that in 2D, you have, for example, 6 slices for one patient. If you want to train a 3D network for to segment the heart, the scar and the heart in this patient, all these 6 slices will be combined into one volume. So it will represent only one sample to train the network, which means substantial reduction in the number of samples used to train the network. And weighted loss function did not help us to improve this problem. So we had to get around this problem by doing something which we know from classical image processing techniques, that we use sliding window approach. We, instead of working on large volumes, we split this volume into smaller subvolumes. So we had, in this study, we had 3 slices only, and then we slid the window on the entire volume. So we compromised the problem of having 2D, where there is no interslice information coming into the network, and the complete 3D, where you have the entire volume represented as one sample to train the network. And this solves the problem. We had efficient training of the network. We got improved segmentation of, or improved sensitivity to detect scars in the images, and we corrected this underestimation of the scar volume. Another challenge that we faced, or another issue that it came to our attention when we did this work, and was raised actually by the reviewer of this paper, is the performance analysis. So the performance metrics, if we have this image and we want to segment the heart in this image, so we can go and do it with manual segmentation. So we get this red binary or segmented image, and then we can feed this image to the network, and we get this blue segmentation. So we need to compare them. In computer science, the most common way of comparing them is to compare the overlapping between the two segmentations, X and Y. So we get the intersection between them and divide them by the total number of pixels. And a good segmentation performance would be having a DICE index of 75%, for example. DICE index could be used for, or DICE score could be used as a loss function, or could be used to evaluate the results of the segmentation, the final testing results. However, in our application, we could not use DICE. Actually, we use it, we reported it, but the problem is it's not that useful, because let me show you this cases. We have two patients here, and we have this image segmented. The yellow part is the scar, red contours are the myocardium, and this is the automatic contours generated by the network, and this is the manual contours. If you give this image and this image to an expert cardiologist, he would say this is perfect segmentation. I mean, there is very strong agreement between the automatic and the manual segmentation. However, from a computer science or computer engineering point of view, the DICE index is 0.37, which means it's failed segmentation. So using improper metric for developing the network or for evaluating the results can be misleading. And we should consider the target or the goal of our study, if it is to improve or to have some clinical significance, then we should pick the performance metrics that match this goal. Other challenges that we encountered, and still encountering it, is to extend the utility of your trained model to more imaging centers, more imaging protocols, or different cohorts of patients or populations. So I showed you that we used dataset from different sites to train a model, but how about trying to extend the use or the utility of this model to a different site, for an additional site? Yes, you can have here 7, 8, whatever, 50 sites, but still there will be a different site that you might need to use this model to segment or to quantify the scar in images acquired in a different site. So this is one problem. Yes, you can use transfer learning, domain adaptation, but then you will probably find some problem in the privacy issues, or some cultural thing, that the ownership of the data. You have data set, can you give it to some other site to refine the model training, or to start training from scratch? So these questions or this represent a real challenge in clinical research, or in translational research. New imaging protocols or updates of scanner. Probably you have a dataset, large dataset, you trained the model, you have a perfect model, but then you update or upgrade the your scanner. You go from 1.5 Tesla scanner Philips, you go to 3 Tesla Siemens. So the images acquired by a different scanner have different characteristics, and your model becomes suboptimal, even if you spend a lot of time to train it and optimize it. Imaging sequences, every few years you get a new imaging protocol, and the differences between the images are really big. Like for here, for this example, this is images for pigs, for the heart of the same pig, using 3 different imaging sequences, and you can see that the contrast of the scar is a bright spot here. And here, this region is a scar, and this is the scar in this sequence. So substantial difference among the different imaging sequences regarding the scar appearance and the background appearance. If we use the data set from one disease, from one patient cohort, it doesn't mean that it will work in other diseases. So scars is not just for HCM. It appears in the myocardial scarring in general appears in different diseases, including myocardial infarction and other non-ischemic cardiomyopathies. So if you have one model trained on HCM, it probably would be difficult to just do transfer learning to a different patient cohort where the characteristics or the shape of the scar itself is different. Finally, the population. Currently, we have different commercial products for segmenting the not the LGE but CENI sequences in MRI. But it's based on, I think one of them is based on UK Biobank, and other products depend on local data sets. The population, probably North America or Europe, this doesn't mean that the even if you purchase this package or the software, it doesn't mean that it will work in your population. So we need, or each community needs to start building its own national repository of images and datasets to enable building its own software packages or deep learning based algorithms. So in summary, deep learning research in radiology and medical imaging is accelerating rapidly. Only few deep learning algorithms can be used in clinical practice, and therefore more translational research is needed. Focus on the clinical value and the applicability in practice. Of course, continuing developing the technical part, the algorithm itself, is very important, but I believe that we have a very large number of algorithms and ideas that are not yet validated or tested in practice. Future directions and opportunities is, I mean, it's open research area. Extending the utility, I think this is one of the most important things that people should focus, and we should all invest more time and effort to try to extend the utility of validated and established deep learning models in clinical practice. Also, I hope that we can design the deep learning models based on principles of medical physics and clinical expertise, instead of getting off-the-shelf pre-trained models or architectures that were developed for example, segmenting natural scenes or used in other applications, and just bring it and use it in on medical images. Probably there is opportunity to design a new architecture to serve your specific application based on your understanding of the problem. Success key factors include establishing strong collaboration between engineering and medicine domains. In literature, you find a lot of very nice computer science papers with good results. However, they are not applicable because the researcher is very smart, very intelligent, but he closes the door, he or she, by the way, closes the door and try to implement this nice idea based on small data set or data set publicly available on the internet, but the clinical value or the importance or the significance of the findings are not considered in this process, which limits the progress of deep learning based research. I believe also we need to continue focusing on the foundations of machine learning and deep learning. So students need to study, to have strong background on statistical analysis and foundations of machine learning, because some people think that it's easy to learn deep learning. The source code is available. We can just use it off the shelf and we get some results. But this doesn't help advance the field of medical image analysis. And also we need to invest in deep learning enabling infrastructures, not just the computational resources, but the process and the pipeline of data collection, cleaning, and storage. Actually, we spend more than 70% of our time in one project just to collect the data and clean it and understand the data that we have. Finally, I would like to thank you all for attending this presentation. I want to thank my colleagues at the Translation Imaging Lab, especially the director, Dr. Nizafat, and our collaborators at Tufts Medical Center and University of Toronto, and my supporting research grant. Thank you so much.
Thank you very much, Dr. Fahmy. It was really an informative talk, and I enjoyed it.
Thank you.
And actually, I support your comments about the importance of having domain experts to be part of the development of deep learning algorithms or techniques, because this is actually a problem which we're seeing a lot. Like you have computer scientists and engineers working on solutions which will never succeed in practice. So I think this is a very important comment. So do you have any questions or comments from the audience for Dr. Ahmed Fahmy? Just please raise your hands, and yeah, I'll let you have your chance. Mr. Muhammad Ilmana, okay. Just a moment. اوكي محمد، ممكن تتفضل حضرتك تقول السؤال بتاعك؟ محمد المانع او المانع.
الو، السلام عليكم.
عليكم السلام، اتفضل.
Thank you, Doctor, for the presentation. My question is how we can handle the issue of segmentation for a high number if we want to build a model, but we can't find experts who can handle the segmentation issue. So how is there any other alternative so we can handle this problem? Thank you.
Yes, I mean, there are many, there are other alternatives if you don't have manual segmentation of the data set, but they are all suboptimal. Like you can have segmentation based on, it's called weak learning, I think. So you can train based on a label of the entire image. So you can show the network cases and you train it and say, okay, this image contains scar, or this image does not contain scar. And you try to see the decision, the heat map that generated this label, whether there's a scar or no scar, and use this heat map as a rough estimation of the input images. However, I don't think in in clinical practice, people would accept this because the accuracy, the resulting accuracy, is not acceptable by the medical doctors in general. You can do this for other applications. Probably you need to have rough estimation of some object inside the image, like whether it's in this location or in that location. But in medical images, you need accurate segmentation, which I don't think. So the answer to your question, yes, you can do it. But in medical image analysis, I think there's a long way to apply these methods in this medical field.
Thank you. Any other questions from the audience? Okay.
Yes.
Sorry. Okay. Hadid, اتفضلي.
Yes, when we're talking about the 3D convolutional neural networks, we said that we have a stack of slices, and now how are we going to predict that it has a score or not if we're going to look only at the stack of slices and not the whole contour to be able to say that this person has a score, for example?
Maybe let me go back. So here, so it's the same thing. You have an input volume, and the output is the segmented volume.
Yeah.
So it's the same thing. You have pixel-wise labeling of each pixel in the input stack to indicate whether there is scar or not, or there is normal myocardium or not at each pixel.
Yeah, so, I meant when we're doing the sliding window technique.
Oh, okay.
We're not looking at the whole.
Yeah, here, yeah. So, okay, let me talk more about this block diagram. So you have 3 slices, okay? You feed it to the network, okay? So you have these 3 slices, and you get this segmented subvolume, right?
Yes.
And then you slide the window here, and you get the subvolume, and then you feed it to the network, and you get this segmentation, right?
Yes.
And then you slide it again to get this subvolume and get a third segmentation. So in this case, for the first slice and the last slice, you have regular segmentation. For the middle slices, you get more than one segmentation for the same slice because of the overlapping of this sliding windows. So we combine these subvolumes together using the mean value, okay, for the myocardium and the blood and the background, and the maximum probability for the scar to improve the sensitivity to presence of scar. And then we generate a one segmented image for each input slice.
Okay, thank you.
So we have several subvolumes. We get several segmented subvolumes, and then we merge these subvolumes together to get only one stack of segmented images.
Okay, thank you very much.
We have another question from Dr. Mustafa Al-Attar.
Mustafa,
please go ahead.
السلام عليكم. ازيك يا دكتور؟
الأخبار؟
Alhamdulillah. Just yeah, maybe I would let the audience know that actually Dr. Ahmed Fahmy was my supervisor during my master's degree at Nine University. That was actually like 12 years ago. Is that correct? Yeah, almost 12 years. So as usual, it's really important to me to know your opinion about one of the hot topics at this in that time, which is actually during the current time, that about the quality of the imaging itself. So I knew that multiple groups in Cambridge and other famous universities, they are focusing on assessing the quality of the imaging modality itself, like to make sure that we have enough quality for further post-processing or maybe segmentation tasks. So can you find a room for this for our application on cardiac MRI, like the diagnostic part of it?
I'm not aware of these studies that you refer to, but in what I can say from the our own studies is that image quality makes big difference in the performance of the neural networks, and we actually we suffer now from limitation in our pre-trained model, which was actually our first model that I presented here. It was trained on old dataset, low quality dataset. So
Okay.
the performance on low quality images were limited, okay, because of the noise. I mean, noise on image artifact introduce variability that you cannot learn because you don't have balanced that set of cases with artifact and no artifacts. So it limits the performance. However, when we tried it on dataset that was properly acquired on properly upgraded or more advanced scanner, recent scanner, using PISR, phase-sensitive inversion recovery image sequence, the images are clear, clean, and you can identify visually, you can identify the scar. So the performance of the network was improved significantly with less amount of data. So yes, image quality plays a very strong, is considered a very important factor in training the networks. But the problem again is extended utility. If you train your network on high quality images, then probably you will get a very good publication because the performance is good. However, taking this model and try to use it on a different center, which might not be fortunate to have this fancy scanner or high image quality, then you get very bad performance. So
okay.
yeah, so probably I would think that probably you can evaluate the input image quality and then branch the segmentation into different models, trained on low quality and another one on higher quality, and then you can just make use of detecting or evaluating the image quality before you do the segmentation.
Yes, I believe that, yeah, this is what I was thinking of actually, that there's a couple of architectures like split brain architectures or autoencoders, that they have different like blocks to learn from different perspectives. And then there's like one thing that combines all the knowledges at the end and stack them in a way or another. So I believe that fits what I'm thinking of. So thanks a lot for giving that help. Thanks.
Okay, you're welcome.
Okay, thank you, Dr. Ahmed and Dr. Mustafa. We have another question from Lamia. Please go ahead.
Hi, can you hear me?
Yes.
Okay, so first of all, thanks for the nice talk. It was really good.
Thank you.
I was hoping for some advice about like how to get the data, because as independent researchers, we usually like get what we have on the internet, and it's either not diverse, not big enough, all these problems. So how do we get the bigger, better, more diverse data? Do we like approach the medical centers? What do we do? I'd like some advice on that.
Yeah, I mean, you said it. You go to whatever school of medicine in probably Asr and Shams, Department of Radiology usually has a lot of and accumulated data sets over the years. But this, I mean, this is the bottom line. You have to go there and talk to them and properly convince them that you can help them to properly publish or properly solve some standing problems they have. But then your problems will start after you get this access to dataset, because you'll have datasets probably not segmented. You don't have ground truth. The reporting of each case may not be structured. Actually, it will not be structured, but it might be not consistent or written in clean way that allows you to build your models. So, but I think it will pay off if you go there and you get a large data set and start working on it for properly. And you need to know that you will spend probably 6 months, probably 8 months just cleaning the data and probably reducing the size of the data from 1,000 cases to probably only 300 or 200 cases that are useful for model training. So, but people need to take these steps because without data, all deep learning development is useless. Actually, let me say it this way.
So do the doctors typically like expect me to like put their names on the publication or maybe give them some prototype that will help them? They don't just give the data for free, do they?
Of course. I mean, yeah, actually.
That I don't have any experience in that, so I'm hoping you could like help me to start.
Okay, imagine that you have your own personal pictures. I mean, whatever, in celebrations, in parties, with your colleagues at the school or something, and then someone is telling you, okay, if you give me this set of images, I will give you no, I'll give you a big thank you. So would you give it to him or her? I don't think so. So you need to get something, may not be like materialistic or something, probably just that you convince him or her that you would help the humanity to or that you're going to do serious research to help reducing suffering or something from the patient's or the doctor's side. So yeah, but I think they deserve to be on the publications because they collected the data, they know that, and actually, okay, again, this takes us to the point that Dr. Muhammad mentioned it. You need to collaborate with them, not just taking the data and thank you. I mean, you'll not get real results that are applicable with only taking the data and using your computer. You need to talk to them. You need to refine the objectives of your results or your project. As I mentioned, if you work on DICE index only, probably you'll be getting frustrated and you'll say, okay, the study is or has failed. But if you talk to a doctor, he would say, no, this is perfect results for us. So you need to collaborate with them, not just taking the data.
Tamam, thanks a lot.
Okay, thank you, Dr. Fahmy. Actually, I think we have to stop here. I mean, it's quite an interesting talk, and we're getting questions. But I give myself the last question.
Okay, sure.
As a chair, okay. Actually, it's related to the last point you just mentioned about using DICE to evaluate your results. I mean, I think there is a problem in medical imaging in general, which is related to how confident we are in the results we're getting during testing, actually. So have you thought about this? Like do you plan to take this into consideration, like having some confidence metrics in your results?
Yes, actually, in one of current studies, we do subjective evaluation of the results. So we show the doctor the contouring produced by the network, and he decides whether this is good or I mean on a scale from 1 to 5, in order to add some clinical perspective of the results, because you might have good agreement in terms of correlation analysis or slope of the linear regression, for example, but you have cases or outliers that that you need to identify, and you need to ask yourself why the network failed in these particular cases.
Yes. Yeah.
So yeah, you can. Currently, we are doing it subjectively, like confidence in the, because okay, one step backward. If you have image and you give it to a doctor and ask for segmentation, he would segment it and give it to you. But then you ask him or her whether he's confident in his segmentation or not on a scale from 1 to 5. Usually in our application, probably in other applications, it's more confident, or they are more certain in their segmentation. But in our case, probably you'll get score 60% in the cases, because it's really challenging even for manual segmentation. And so you have uncertainty in the ground truth on the reference segmentation that you use for training. And then you have added uncertainty for the produced by the network. So you need to, I mean, if you are going this way of quantifying the certainty or the confidence in the segmentation, then you need to first evaluate the confidence in the ground truth, and then move to the confidence in the automatic segmentation. People are using, I mean, because, okay, in some applications of probably classifying the patients or grading the severity of a disease, you may go to heat mapping or heat maps to see the, and there are, I think, a number of studies used heat maps to assess the certainty in the on the network decision. But in segmentation, I don't think we need this heat maps, because you can see the output on top of the image, so you can subjectively, you can evaluate it. In classification or disease identification, it's a different story, because you don't know, or you cannot explain, or you want, or you need to explain why the network identified a disease in this case, but not in this case. What was the factor? What was the set of factors that directed the decision of the network towards a healthy or a diseased subject? So in this case, yes, you need to explain the decision of the network and assess the confidence in this trained model. In segmentation, I don't think we need this, because you have the input image, and on top of it, you have the output of the network. So you can simply know whether it is you have confidence in this output or not.
Okay. All right. Thank you very much for this nice presentation and discussion. And
thank you for giving me this chance. Yeah, I really
you're most welcome. And thanks for all the attendees, and hope to see you soon in another session. Thank you very much.
Thank you.
Okay. Bye-bye.